Question 1. This question is about gravitational potential energy. Diagram below shows a planet of mass m and radius rp. The gravitational potential V due to the planet X at point X, distance r from the center of the planet is V is equal to minus gm by r, where g is the universal gravitational constant. Now, show that the gravitational potential V can be expressed as this, where g0 is the acceleration of free fall at the surface of the planet. Okay, so at the surface of the planet, gravitational acceleration is g0. Now consider or imagine there is a planet, right? Planet X of mass m. It is at this point. Okay. Now the force exerted, gravitational force exerted. See the distance between these two. What you can do is you can consider this to be point mass. This is a better. Can consider this to be a point mass and bring it here. Okay. Now the distance, this is having mass m. Now the distance is rp because the radius is rp. So distance from here to here is rp. Now rp, now force, gravitational force F is equal to, I'll write it here instead. F is equal to mg0. Makes sense? Force into mass into gravitational acceleration, mass of the object and gravitational acceleration. Now, from Newton's law of gravitation, we know it. Force is also equal to gm small m by r square. R here will be rp. What is m? What is this big M? This is the mass of the planet. And we are assuming that the mass of this planet is concentrated at this point. Okay, with m mass, m kg. Now you see m gets cancelled, so we are left out with gm is equal to g0 rp square. Okay. Now v is equal to minus gm by r. R is the distance from here to here. Originally, obviously, we are assuming that this planet is here, but originally the planet is actually at this point, r distance away from the core of the bigger planet. Okay. Now gm, we got to know is g0 rp square, g0 rp square divided by. So we are able to show that v is equal to minus g0 rp square divided by r. Now B part, the graph below shows how the gravitational potential V due to the planet varies with the distance r from the center of the planet for values of r greater than rp, where rp is this much. Now the radius of the planet, they are saying rp is equal to 2.5 into 10 to the power 6 meters. And we know that from core to this point, the potential remains constant. And then it starts varying. Okay, so V is constant, and as you can see, it is around this much. This much. Now, when R is equal to radius is equal to RP, V is equal to, as you can see, it is 9 point. The magnitude of V is, or I'll write minus 9.246. 9.6 into 10 to the power 6 joules per kg. Rp is 2.5 into 10 to the power 6 meters. Now we have found out V is equal to minus G0 Rp square divided by R. Right. Now you see R we are considering because we are imagining that. I'll draw it here. We are imagining that the smaller planet has come to this point. Okay. First we are assuming that smaller planet is concentrated in one point, and we are assuming this to be point mass, and it has come to the surface of the bigger planet. Okay, from here, the center of this bigger planet to here, it is Rp. R we are considering. R is nothing but the distance between the core of the bigger planet to the smaller planet. So we are considering, in this case, we are considering R to be Rp. So we put G0 Rp square by Rp. So Rp and the square gets cancelled. So finally, G0 is equal to minus V by Rp. Now V is minus 9.6 into 10 to the power 6 joules per kg, and Rp is 2.5 into 10 to the power 6. So this one gets cancelled. This minus minus becomes plus. So we are finally going to get 9.6 divided by 2.5, which is 3.84. 3.84 meters per second square. This is the G0. Or you can also write it in terms of Newton per kg. So on every kg on the surface of this planet, 3.8 Newton force will be, gravitational force will be exerted. So let us write it down here. G0 is 3.84 meters per second square. So G0 we have found out to be 3.84 meters per second square. Okay, so this is the answer for this question. Now, next question. Second question, show that the minimum energy required to rise a satellite of mass 3,000 kg to a height of this much above the surface of the planet, about 1.5 into 10 to the power 10 joules. So basically, they're asking us to find out the work done in order to rise a 3,000 kg mass satellite from the surface to a height of this from the surface. Okay. So work done is actually change in potential energy, which is equal to mass of the satellite, mass of the smaller object into del V, change in the potential, gravitational potential V. Okay. Now, what is the change in gravitational potential? So, initially it is at 2.5. So, initially V0. So, we want to find out del V first. Where the del V is V0 minus V final. So, V0 we have found out to be 9.8. In the previous question itself, we have found out to be 9.6 into 10 to the power 6 minus V final. Now, you see, they have particularly told 3 into 10 to the power 6 meters above the surface. That means from this point onwards, you have to add 3. So here it will be 2.5 plus 3 is going to be 5.5. 5.5 is going to be somewhere here. This is 6. This is 5. So 5.5 is somewhere here. Okay. So at this point, gravitational potential is 4.2, 4.4. So 4.4 into 10 to the power 6 joules per kg. Why did we add this plus 3? Because they're particularly asking 3 into 10 to the power 6 meters above the surface. So 2.5 from core to surface is 2.5, and you have to add 3 more to get the final distance from the core, which is 5.5 into 10 to the power 6 meters. Okay, now solve this one first. 9.6 minus 4.4 is 5.2. 2 joule into 10 to the power 6 joules per kg. Now we want to find out the work done, which is del U, which is mass into del V. So mass is 3000 kg for the satellite. It's mentioned here, 3000 kg into 5.2 into 10 to the power 6 joules per kg into 3000 into 10 to the power 6. We are going to get 1.5 into 10 to the power 10 joules per kg. So this 1.156 into 10 to the power 10 joules per kg, which is definitely close to 1.5. We are actually correct. Maybe if you consider this del V, V0, plus minus 0.2, plus minus 0.2, you will be able to get the proper answer. Very much close to 1.5, since we have found out this to be 0.96 for 9.6. So we are getting 1.56. That's the correct answer. No problem with that. Let's go close to this. So where did we make a small correction can be made? See, this is not a mistake. This is small correction. See, this line is not perfectly touching this line. So it is little less than 9.6. So if we consider that, then it's going to be correct. You are going to get exactly or very much close to 1.56 10 to the power 10. Anyway, this is how we solve it, and this is approximately correct answer. So yeah.